Hi, my name is Uzair Maghrabi, and this is my vision-based indoor positioning system. But first, what is an indoor positioning system? An indoor positioning system, or IPS, is a way of localizing an object within an enclosed space. The two main IPS methods used today are beacon-based localization and odometry-based localization. Beacon-based localization involves placing beacons in known positions and sending signals between the beacon's transmitter and the robot's receiver. By measuring the time of flight of the signal and using multiple beacons, you can triangulate the position of the robot. Odometry-based localization involves using precise wheel encoders to measure the rotation angle of the wheels, allowing you to calculate the distance a robot has traveled from its starting position. However, these methods become unreliable in real-world environments. Beacons can lose signal or be blocked by moving obstacles in a dynamic environment, while odometry suffers from accumulated error over time, for example, due to wheel slippage and the lack of a closed control loop. So I decided to design a low-cost IPS that works in dynamic environments and incorporates a closed control loop to correct for errors. For this task, I chose to use computer vision. I chose computer vision because it provides a global perspective of the environment, allowing the system to track the robot's exact position. Unlike local sensors, vision systems can see the robot in relation to its surroundings, which makes it easier to detect and correct positional drift in real time. Additionally, allows for flexibility in complex changing environments where traditional methods may fail. First objective was to construct the environment. I built the environment to be modular to allow fast and effective prototyping. The second objective was localization. This involved calibrating the camera and applying a perspective shift to obtain a true top-down view. I then used color filtering to detect green borders which served as obstacles. The third objective was pathfinding. This is where I visualize all the information obtained from the camera in a pathfinding array displayed using the Pygame UI. I also implemented the A-star pathfinding algorithm. The fourth objective was developing a PID control system to manage the linear and angular velocity of the robot. The final objective was to transmit information to the robot over Wi-Fi using a local MQTT broker called Mosquito, which I installed on my computer. For the hardware implementation, I built an enclosure using custom 3D printed corners I designed in Fusion 360, and I mounted an ultra-wide camera in a top-down view over the environment. I also designed a differential drive robot with an ESP32 to receive instructions from the system. I chose the ESP32 because of its built-in Wi-Fi capabilities, which allow me to send positional information to the robot. Since the system is intended for real-time use, it's important that the code runs concurrently to minimize latency and improve processing speed. To achieve this, I use parallel processors. The main loop processes video frames, while two additional processors handle the visual UI and data transmission to the robot. One major challenge I faced was object detection. Due to uneven lighting, light artifacts in the frame sometimes appeared as objects, causing false positives. To address this, I applied a Gaussian blur to smooth the frame and used contour filtering to eliminate small noise. To send information from the system to the robot, we will use Wi-Fi. The most popular Wi-Fi communication protocol for IoT devices is MQTT. MQTT uses a publish and subscribe model. The MQTT broker is responsible for establishing connections and distributing messages, enabling effective data exchange and bidirectional communication. We will use a Mosquito service to create an MQTT broker on my machine. As for future improvements, I would add a smarter object detection system to autonomously identify areas of interest within the environment. This would completely remove the need for human input, enabling full autonomy. I could also expand the system by adding additional robots to the environment. This is a relatively simple enhancement, as I can assign a new Arugo marker to each robot. This could significantly boost productivity, especially in environments where staff are overburdened, such as hospitals. Lastly, I can implement an auto-tuning PID algorithm to automatically adjust the PID parameters. This would further improve efficiency and response time, regardless of changes in an environment. To conclude, I successfully designed a low-cost vision-based IPS that can operate in real time within a dynamic environment. I designed both the environment and the robot and used multiple image processing techniques such as perspective transformation and color filtering to achieve this. I also developed a PID algorithm to control the robot. Throughout this project, I gained valuable knowledge about autonomous robotic systems, including waypoint navigation and obstacle avoidance algorithms like A-star. Thank you for listening to my presentation. Now I'll show you a demonstration of my system in action. Now that the system is running, we can see two displays. On the right is the frame captured by the camera. We can see that this frame is a true top-down view of the environment, allowing us to see the robot and any obstacles, in this case the green balls. To achieve this, I had to correct for any camera distortion and apply an image transformation using the Aruka markers in the corner of the environment. I've also displayed the FPS on the system, which is averaging around 30 FPS. Since I want the system to react in real time, having a high FPS is important. Using this frame, we can use color filtering to detect any obstacles and also mark the location of the robot. All this information is passed into an array and sent to the Pygame UI process. On the right side, we can see the Pygame UI. We can see that the environment has been split into columns and rows, with each node in the grid having a different color. Green represents the location of the robot, red represents the location of the obstacles, and white indicates clear space. As these two systems run parallel to each other, information like obstacle position detected by the main code will simultaneously be updated in the Pygame UI, as I will demonstrate. To set the destination point, we have to select a white node using our cursor. If we try to select a green or red node, an error will pop up. Now that we have selected our finishing node, a blue box will appear on the Pygame UI. To clear the finishing node, we can press the Clear button. Now, all that we have left to do is press the Start Pathfinding button. This will calculate the most efficient path to the destination points using the A-star algorithm. This information will be sent to the PID process, which will calculate the linear and angular velocity necessary to drive our robot to each waypoint. This information is sent to the ESP32 via Wi-Fi. Now let's see in action. As you have just saw, the robot avoided the obstacles to get to the finishing point, in which the robot followed these waypoints. These waypoints are in the shape of a B-spline curve. This is to ensure that the robot control is smooth and accurate. Also, the path has been displayed on the Pygame UI using a yellow box. We could also see the robot's progress through the path. Now, we can test out something I like to call the dynamic obstacle avoidance. We will set everything up as before and press the Start Pathfinding button. However, while the robot is navigating through the environment, I will place an obstacle in its way. The system will then detect that an obstacle is in the path and a new path will be given for the robot to follow. As you have just saw, I placed an obstacle in its path and the robot received a new set of waypoints to avoid that new obstacle. We can see in both displays that the waypoints, as well as the Pygame UI, updated to fit the new path the robot will take.